Hello and welcome to a brand new episode of IEEE Pune's podcast Beyond Conversations. Recently, I came across an article that spoke about micro robots walking with electronic brains, no external controls whatsoever. Now, whether that's fascinating or frightening is a huge topic of debate, but we can all agree that innovation is bounding exponentially in the field of tech. It's like humans are making magic with the help of math and algorithms, and electronics is at the very core of this innovation. On today's episode, we have with us Maithilee Kulkarni. She is a graduate in computer and electrical engineering from the University of Texas. She's been working in the fields of computer architecture and machine learning for about 3 years in California in the Bay Area. And we're going to talk about really interesting aspects about her education and her career and her knowledge in the field of computer architecture and electronics. Welcome to our show, Maithilee. It's great to have you here. So let's begin with the questions. So when did you decide that you wanted to pursue a career that's so aligned with computer architecture and machine learning?
Yeah, so I graduated with bachelor's in electronics and telecommunication. So we had been taught courses both in electronics and telecommunication, but the electronics side sort of intrigued me more. And I took courses in like VLSI, computer architecture, machine learning, even in undergrad. So that sort of triggered the interest, and that is how I decided to pursue masters. And during masters also I got like a varied range of courses, and I got to do research with different professors. So that was also like an enriching experience.
Okay. A lot of youngsters in India believe that it's really fascinating to complete their higher education abroad, especially in the United States. Can you tell us about your experience at the University of Texas?
Yeah, indeed. So as I said, it was like a really enriching experience. So I think universities in the US, they are very well funded for research. They work very close to industry. So academia industry gap is very less. And because of this whole close nature, there are very nice opportunities. So even during my thesis, I got to work with in collaboration with an AI startup based in California. So that was also really good. Other than the thesis, even the courses themselves have like very hands-on assignments and projects. So they are also very good learning opportunities. Yeah.
Okay, so you mean there's more of a focus towards actual practical learning rather than the theory-based rattamar that we go through out here.
Yeah, that's totally true. Yeah.
So as you mentioned, you worked on a research project while you were completing your education. Can you explain what that was about, how the experience was?
Yeah. So the research project was use of machine learning in the verification step of hardware design. So in the hardware design cycle, we have like architecture step, microarchitecture, RTL design, then verification, and then physical design and other steps. So in the verification part, the job of the verification engineer is to come up with the test cases so that we verify that the RTL or the hardware that we built is what we intended to build. And that's a very tough job, and that is where the domain expert knowledge comes into picture. So the idea of the thesis was we will take this burden out of verification engineer's shoulder and let AI do that job. So we will train the ML model such that the ML model itself will come up with the test cases that can be run on the hardware that we are testing. And during that, so there were few open source algorithms. There were few custom implementations of open source algorithms, and there was this reinforcement learning IP that was provided by the AI startup I mentioned. The name of the startup is InZone AI. It's now called as VerifAI. So there
Okay.
were such 10 algorithms that we compared based on like accuracy and convergence rate. So the whole exercise is to improve the coverage in simulation based verification, so that the hard to hit test cases can be generated automatically. So that
Okay,
was
that's
the yeah. He also published a paper in DVCon Europe based on that thesis. So
okay,
yeah.
that's really amazing. I mean, it's very interesting how automation is really taking leaps and bounds these days.
And I think this is still like barely just scratching the surface. We have yet a lot to discover, is what I believe.
Right. So you've been working in two fields that are like at the forefront of automation, electronics and machine learning. So do you see a confluence between them?
Yeah, totally. So the math behind ML algorithms or the statistics that existed for quite a few years, but the reason of this being like forefront of the technology right now is I feel the availability of bigger data sets, cheaper memory, and one of the main contributing factors is the much better compute capability. So we
Right.
have much better hardware now, thanks to Moore's law. Although Moore's law, it is said that Moore's law is going to saturate now, and that is where I think the newer architecture and microarchitectural aspects will come into picture, and that is where this new field of coming up with specific hardware for a specific application that has started to grow. So we have these GPUs, graphic processing units. So the moment we realized that this can be used for a general purpose machine learning training model, so that was like I think sort of the inflection point in this whole field. So GPUs are one example. There are also these newer hardwares. For example, NPU, neural processing unit. Then there is DPU, data processing unit. Pensando is, for example, doing it. Then there is CGRA, which is coarse grain reconfigurable array. Stanford is very active in this whole field. So they have a group called Agile Hardware Architecture. They are involved in this CGRA business. There are also IPUs, which are like intelligence processing units. GraphCore is a startup in that field. So, in short, like bigger growth and good days ahead. So, this is all about like hardware for AI. There are also, I forgot to mention, there are also a few startups in Edge AI inference field. So Edge AI Inference Accelerator is a very interesting field because they have a constraint of performance and power both. So they are not just concerned about like throughput or latency; they are also concerned about low power. So performance per
Right.
watt is their sort of metric. So there are very interesting things that are coming up in that field. So this is all about like hardware for AI. We also have AI for hardware. That is where actually my thesis was in AI for hardware field. There are other few things in that umbrella. For example, we have like design space exploration in EDA tools. So EDA tools are these tools by you must have heard of Samsung. You must have
Yes.
heard of Synopsys and Cadence Virtuoso. So
Yes.
these tools now use machine learning for like place and route and different congestion algorithms for which are ML assisted. So yeah, this field is like emerging like anything now. Yeah.
Okay, so that's the reason why, especially in the 2020s, electronics is seen as one of the top fields in tech.
Yeah, that's right.
So I'd like to ask you, beginners find it really hard to foray into the world of machine learning, especially because there's a lot of different algorithms that you can use to, work on different data sets. So how did you start out? How do you keep yourself upgraded about all these processes, especially because it's a very dynamic field?
Yeah, that's right. So starting point for me was the university courses, but soon I realized that it's not sufficient. because what we have been taught in schools is usually like the algorithms, the basic of it, like regression, for example. But people have reached to transformer now. So no, like people hardly use regression in industry today. So the only way to keep yourself relevant is keep reading like new papers, new keep attending new conferences, whatever is like virtual, free, go and attend it. There is a running joke in this field that any state-of-the-art implementation is only state-of-the-art for only 3 weeks because it's so fast-paced and so much fast changing that you to keep yourself relevant is like very, very important. But yeah, as a starter, maybe solving classical problems in each field can be like a good starting point. For example, like MNIST data set is very famous. It's handwritten digits recognition. So that could be like one starting point in like CV field, for example. Or there is this tokenizer or sentence boundary problems that are for NLP field. Then there is famous like classical problem of cocktail party problem for principal component analysis. So like these are field specific problems. So just take them and like code it right from the scratch without using libraries. Then maybe solve it for a difficult data set using libraries like TensorFlow, PyTorch. That could be like second step. Third step could be usually the papers published in URIPS or CVPR or any other good conferences. They have like a Git repo corresponding to them. So usually everything is open source. So just go to that and try to implement it yourself. So these could be like the points.
Okay, so basically your resources you would say are research papers and their Git repositories.
Yeah. Of course, after you are done with the basic course and understanding of the like the math behind it. Yeah.
From an industrial perspective, what do you think are some of the concepts that you really need to know, both in electronics and in machine learning?
Okay, so I can talk about myself. Like
Right.
in my day-to-day job, I really need like first of all computer architecture concepts, architecture and microarchitecture both. Then a little bit understanding of like end-to-end flow of how this whole semiconductor industry works. So
Right.
like I already mentioned the steps, right? So the end-to-end flow like from architecture to silicon, and then post-silicon validation and like actually giving the parts to customer. So that bird eye view basically of this whole end-to-end flow. So these two things are like super important from hardware perspective. From software perspective, of course, coding skills are important. So in general, like my day-to-day job involves like writing performance modeling tools, power modeling tools. So coding is like super important, and maybe lead code could be one way to do that. That and for ML, I think I already mentioned about these courses. A lot of material is available even like on YouTube. All the important like all even EDX Coursera, many courses are free. So doing
Right.
them, but with assignments, of course. So these are sort of like the key things. Yeah. So I think hardware software co-design, people have understood its importance now. So it's everywhere. Like even if you go in a software field, which are in this domain, training inference domain, they also need to know about hardware. We also need to know about what's going in the algorithm or software. And a fundamental difference there is software like design cycle, life cycle is very short. If you can launch something in 6 months, that's not true with hardware. Hardware, the design cycle is like around 2 years from the day we decide to 2.5 years, like till the part comes and gets shipped to customer. So
Right.
the point is, while we design hardware, we have to predict what kind of software will go 2 years down the line. So that's the kind
Yeah.
of gap, and once we realize like that's the key thing, the like things get easier.
Right. So you've been working in the industry for around 3 years. Can you describe one of the most exciting projects you worked on?
Yeah, sure. So one of the main projects I worked independently on was NOC, that's Network on Chip. So I work in FPGA architecture team, and NOC is like the central part of it because it connects the processor subsystem, AI engine that's like our own ML accelerator that we have on chip, and also the FPGA fabric and memory subsystem. So because I was working on NOC, I sort of got a system level perspective of the hardware that we were designing. And this involved a lot of like skill sets. So one thing was we abstracted it to a directed graph, and a lot of graph theory concepts that I learned during school I could use in my day-to-day job, and that was fascinating because I always thought graphs is something like they ask only during interviews.
Yeah.
So that was one major thing. Another thing was because it was a system level thing, I understood like how the power performance area trade-off that plays in the design design thing. So even if we improve like one part of the chip to the max extent, the system performance might not get affected. And that was a very hard learning lesson. So no, on the network on chip design, its architecture and modeling, that was like the most exciting thing that I have worked on, and I'm still working on it for next generation architectures.
Okay. Speaking about interviews, what do you think are some key aspects that you need to know about when going through an interview that's especially for machine learning and computer architecture?
So actually a lot of it depends on what stage you are interviewing for. So if you're interviewing for like fresh out of undergrad, they will expect you to know mostly like the basic concepts should be clear: digital design, of course COMPARC, and in COMPARC like virtual memory, caches, how does that kind of thing work, paging, how does paging work, little bit of OS concepts also. So all of that. Then if and of course for machine learning, actually I have not appeared for any interview right after undergrad, so I don't know. After after masters, for this position that I am working at, I was interviewed for, I think, there were 2-3 rounds during on-site, 2-3 types of rounds during on-site. One round was specifically for these architecture concepts, one round was specifically for coding, just lead code type of questions, and one round was specifically for the ML stuff. So the ML stuff that they asked during interview, it was more like open-ended. So they would give like the kind of data set we use in the day-to-day life, and then what kind of algorithm would you use? Would you rather go for a classification over regression and those kind of questions? So
okay.
Yeah. But for a complete ML role, the questions might be different. This was more like a hardware software co-design role.
Okay, so you're saying you would have to have a combination of both of those things, the basics of both.
Yeah, that's right.
And the ability to predict, what you should be using, what algorithm you should be using for a particular problem. And that will come obviously through a lot of practice.
Yes,
right.
That's right.
So we spoke about your favorite project.
I think even with...
Yeah, go on.
Yeah. No, I was just saying that's true even with lead code. Like the kind of problem and the kind of algorithm you use, that mapping comes automatically to your head only if you do like certain number of problems.
Right. So the first step is expanding your knowledge as much as you can, and then implementing it on a practice basis, and then going and showing it off.
Yeah, right. That's right.
Okay. We spoke about your favorite project. We spoke about a lot of concepts that you need to know. You said that about the flow. What is the flow of actually, producing chips and then sending them to the customers? Can you speak about what your day-to-day job and everyday job consists of?
Yeah, sure. So one major thing, as I mentioned, is writing the tools. So usually the performance modeling tools, it's mostly in System C and C++. We also have some local internal stuff that goes in Python, but production is always like C++. These Python tools are where we experiment. So, for example, in case of knock, we have this static analysis tool that we extract graph out of it and just work on the graph properties and then link. So every physical link in the hardware is just like a link in the directed graph. So that kind of thing. So this thing goes in like Python. The other what happens at like each cycle. So that cycle by cycle implementation that goes in C++. So in a day, for example, I think 60% of my work goes in like coding, 10 to 20% goes in like debugging and creating, documenting the things that we are doing, and maybe another 20% goes in all the other logistical stuff like creating PPTs out of it, presenting, and responding to email and all of that. Yeah.
But do you find that tiresome? I mean, my father works as software. The entire day he's into meetings and discussing about what needs to be done.
Maybe I think at that seniority level, it might be tiring. It's not tiring right now because no one is like sort of dependent on me. I am dependent on people. So yeah, so it's the other way around. Maybe I am the person who like bugs everyone more. Yeah.
Okay. Like we said, there's a lot of automation taking place, but with tech, there comes both hope and despair. So I'd say that based on, let's say, the example of Facebook, which kind of, there's a notion that Facebook uses people's information, manipulates it for their own business, manipulates their decisions in their lives. And that is a part of ML. What ML is being used for is also for manipulation. So one part of it is the good side and one part of it is the bad side. What do you think the direction we're headed in? Is it the right direction?
Yeah, that's an excellent question, first of all. And I think it's not just Facebook, it's like everyone is sort of, people blame every big company for that.
Yeah.
There was also a show named Social Dilemma sometime back on Netflix that went very close to your question. Yeah, I think, I don't know, maybe I just feel it's too early to start worrying about it. We have a long way to go, and there are like positive and negative sides in each part of the growth and part of the tech. So let's just focus on the bright side is what I feel. We have a bright path ahead. And to answer your question about data privacy and security, there are various, I think, laws and rules and regulations that are coming up. There is also a concept of federated learning that's coming up. So that's like your ML model will get trained without any human intervention. So without anyone looking at the data, touching the data.
Right.
So yeah, I mean, hopefully we have like only good things ahead in the future.
Exactly. You live at California in the Bay Area, and that's away from your home, but that's basically in dreamland. People in India really want to go and live in California. The weather is pleasant. It's in the United States of America. What can you say about the experience culturally, socially?
Yeah, so I think Bay Area has a lot of history, especially in tech, because like most of the tech headquarters are here. Like there are amazing peers, amazingly talented people. So you're always surrounded by like bright minds, and it always helps to keep you grounded. So that's like really amazing thing. There are also many networking events here, various poster presentation events that because you are here you can attend, otherwise you couldn't have. So like in terms of professional experience, it's a very like enriching experience to live here. As you mentioned, weather is also like very, very good in terms of like 12 months sunshine, and both beach and mountain are one hour drive drivable distance at 1 hour drivable distance. So that's also really good. But yeah, downside is yeah, I'm staying away from home, and because of this COVID and immigration issues, I haven't been home in 3 years, and that's a long time. So yeah, these things are there. Another problem about Bay Area is high taxes and high cost of living. But I think it's always a trade-off, and if not anything, computer architecture teaches you that it's always a trade-off. If you increase performance, you will have to sacrifice on power, and same thing here. if you want to gain something, you have to lose something.
Yeah.
So yeah, pros
So
and
basically,
cons.
balancing out the bright sides and the downsides
Yeah.
is both a part of ML, computer architecture, and living in Bay Area.
Yeah, that's right.
Okay. It's been great talking to you, having you here, speaking so much in depth about all the concepts that you know of. Signing off, is there any advice you would like to give to people who are working in your particular fields or in general in tech, especially for people who are starting out?
Oh yeah. So I would say I think being curious is like super important, and that's the only important thing. If you're curious, you will go and find out like questions, solutions, new information, new technology in any field. So I think that's like make best of it, make best of your curiosity, and go there. Like basically, it's like this whole world is like full of mysteries. So go on that journey is what I would like to say. And yeah, thanks a lot for this opportunity. It was like really great talking to you.
Thank you.
Thanks.
Thank you so much for watching today's video. If you liked this video, if you found it interesting, please head down to the subscribe button. Please like and share our video and share what you thought in the comments. Thank you. Bye until the next time.